Welcome to AI Fundamentals, How AI Really Works. I'm excited to have you here. Artificial intelligence is one of the most transformative technologies of our time, and it's already changing how we work, learn, communicate, and solve problems. You may have heard terms like machine learning, deep learning, ChatGPT, large language models, or generative AI. These concepts can seem complex or even intimidating at first. The good news is that you don't need a background in programming or computer science to understand them. In this course, we'll break down AI into simple, practical concepts using real-world examples and easy-to-follow explanations. By the end of this course, you'll understand not just what AI does, but how it actually works. Artificial intelligence is no longer a futuristic idea, it's already embedded in many of the tools and services we use every day. When Netflix recommends a movie, when your email filters spam, when Google Maps predicts traffic, or when ChatGPT answers your questions, AI is working behind the scenes. Across healthcare, finance, education, transportation, and many other industries, AI is helping people make decisions, automate repetitive tasks, and uncover insights from data. Understanding AI isn't just valuable for engineers. Whether you're a student, business professional, entrepreneur, or simply curious about technology, AI literacy is becoming an important skill. This course follows a structured learning path. We'll start with the fundamentals of artificial intelligence, including what AI is and how it has evolved over time. Next, we'll explore machine learning, the approach that allows computers to learn from data instead of following fixed rules. From there, we'll dive into deep learning, neural networks, and the technology behind modern AI systems like ChatGPT. We'll also examine real-world applications, ethical considerations, and the future of AI. By the end of the course, you'll have a strong conceptual understanding of AI and the confidence to engage in conversations about this rapidly evolving field. One of the most common questions I receive is whether learners need to know programming before studying AI. The answer is no. This course focuses on understanding concepts rather than writing code. We'll use plain language, practical examples, and visual explanations to make AI accessible. If you're completely new to AI, you're in the right place. If you already have some exposure to AI, this course will help organize and deepen your understanding. It's important to set clear expectations. This isn't a coding bootcamp or a graduate-level AI course. We won't be implementing algorithms in Python or deriving mathematical formulas. Instead, our goal is to understand the ideas behind AI. By focusing on concepts first, you'll build a solid foundation that can support more technical learning later if you choose to pursue it. Learning AI is like learning a new language. Each concept builds on the previous one. I encourage you to watch the lessons in sequence, take notes, and pause occasionally to think about how the ideas apply to technologies you already use. The quizzes and examples are there to reinforce your understanding, so take advantage of them. You might be surprised by how often you interact with AI each day. From unlocking your phone with facial recognition to receiving personalized recommendations while shopping online, AI quietly powers many of the digital experiences we've come to expect. Throughout this course, we'll uncover the technologies behind these familiar applications. Here's a preview of the journey ahead. We'll begin with the foundations of AI and gradually build toward more advanced topics like deep learning and generative AI. We'll also explore how AI is applied across industries, discuss important ethical questions, and consider what the future may hold. Each module is designed to build naturally on the last, so by the end you'll have a coherent understanding of the field. Before we dive deeper, take a moment to think about your current understanding of AI. What examples can you identify in your daily life? What questions do you hope this course will answer? There's no right or wrong answer here. This quick reflection will help you appreciate how much your understanding grows as we progress. Congratulations on completing the introduction. You now have a clear understanding of what this course will cover and how we'll approach learning AI together. In the next module, we'll tackle one of the most fundamental questions: what exactly is artificial intelligence? You'll discover that AI is often very different from the way it's portrayed in movies and popular media. Let's get started. Let's begin with the most important question of the entire course: what exactly is artificial intelligence? In simple terms, AI refers to computer systems that can perform tasks we usually associate with human intelligence. These tasks include recognizing objects in images, understanding spoken or written language, learning from experience, solving problems, and making decisions. Notice that this definition doesn't say AI thinks like a human. Instead, it performs specific intelligent tasks. That's an important distinction. Today's AI is highly capable in certain areas, but it doesn't possess human consciousness or understanding. Human intelligence and artificial intelligence share some similarities, but they are fundamentally different. Humans learn through life experiences, emotions, intuition, and common sense. We understand context naturally. AI, on the other hand, learns by analyzing data. It identifies statistical patterns and uses those patterns to make predictions. Even when AI appears intelligent, it's important to remember that it isn't aware of what it's doing in the human sense. AI can sometimes feel magical because of how impressive its results are. However, there's nothing supernatural happening behind the scenes. Every AI system is built using data, mathematical models, algorithms, and powerful computers. Throughout this course, we'll uncover each of these building blocks so you understand how AI works instead of simply being amazed by it. Traditional software follows explicit instructions written by programmers. Every rule is predefined. AI takes a different approach. Instead of programmers writing every rule, AI learns patterns from examples. This ability to learn from data is what makes AI adaptable and capable of solving problems that are difficult to describe with fixed rules. AI is already woven into our daily lives. Search engines rank results using AI. Streaming services recommend movies. Email providers detect spam. Navigation apps estimate travel times. Voice assistants answer questions, and generative AI tools help us write, code, and create. Once you start looking for AI, you'll realize it's almost everywhere. AI is particularly good at tasks that involve identifying patterns in large amounts of data. It can analyze information much faster than humans, perform repetitive tasks consistently, make predictions, and personalize experiences based on user behavior. These strengths explain why AI has become valuable across so many industries. Despite impressive capabilities, AI has important limitations. AI doesn't have feelings, consciousness, or personal experiences. It doesn't understand the world the way humans do. It generates outputs based on learned patterns, not genuine understanding or awareness. Remembering this helps set realistic expectations for what AI can and cannot do. Nearly all AI systems today are examples of narrow AI. They are designed to perform specific tasks, such as translating languages, recognizing faces, or recommending products. General AI, often called AGI, would be able to learn and perform virtually any intellectual task that a human can. While researchers are actively exploring this possibility, such systems do not yet exist. These three terms are often used interchangeably, but they represent different levels of the same field. Artificial intelligence is the broad discipline. Machine learning is a subset of AI focused on learning from data. Deep learning is a specialized form of machine learning that uses multi-layer neural networks. We'll explore each of these topics in depth later in the course. If you remember only one concept from this module, let it be this: AI is fundamentally about pattern recognition. Whether it's identifying a cat in a photo, detecting fraudulent transactions, or understanding customer sentiment, AI looks for patterns in examples. Those learned patterns allow it to make predictions on new, unseen data. This idea will become the foundation for everything we discuss in the rest of the course. AI is surrounded by myths, often fueled by science fiction and media hype. In reality, AI doesn't think or understand in the way humans do. Its knowledge comes from training data, and it can make confident mistakes. Rather than replacing every job, AI is more likely to automate certain tasks while creating new roles and changing how people work. AI is no longer limited to research labs or technology companies. It's helping doctors diagnose diseases, assisting banks in detecting fraud, optimizing manufacturing processes, supporting teachers with personalized learning, and improving transportation systems. As AI continues to evolve, its influence will only expand across more industries and professions. We've covered the essential concepts that form the foundation of artificial intelligence. You now understand what AI is, what it isn't, how it differs from traditional software, and why pattern recognition is central to modern AI. These ideas will support everything we explore in the upcoming modules. Before moving on, take a few moments to answer these questions. They aren't about memorizing definitions, they're about checking your understanding of the key ideas. If you find any question challenging, that's perfectly normal. Consider reviewing the relevant slides before continuing. Building a solid foundation now will make the rest of the course much easier. The dream of creating intelligent machines is much older than computers themselves. Throughout history, people imagined artificial beings capable of thinking and acting like humans. Ancient myths described animated statues and mechanical servants. During the Renaissance, Leonardo da Vinci designed mechanical devices that hinted at automated movement. Later, science fiction introduced intelligent robots that inspired generations of scientists. Although these early ideas were fictional or mechanical, they planted the seed for what would eventually become artificial intelligence. Before AI could exist, computers had to be invented. Charles Babbage designed the analytical engine, one of the earliest concepts for a programmable machine. Ada Lovelace recognized that such machines could process more than numbers, making her one of the first people to imagine broader computational possibilities. With the arrival of electronic computers in the 1940s, scientists finally had machines capable of performing complex calculations quickly enough to explore intelligent behavior. Alan Turing is widely regarded as one of the fathers of computer science and AI. During the 1930s and 1940s, he developed foundational ideas about computation and helped break encrypted communications during World War II. In 1950, he posed a bold question: can machines think? Instead of debating philosophy, he suggested evaluating whether a machine's behavior could appear intelligent to a human observer. The Turing test is one of the earliest and most famous ideas in AI. In this test, a human judge communicates with another human and a computer through text. If the judge cannot reliably identify which is which, the machine is said to have demonstrated human-like conversational behavior. While modern researchers debate whether the Turing test is still the best measure of intelligence, it remains an important historical milestone. In the summer of 1956, a group of researchers gathered at Dartmouth College for a workshop that officially introduced the term artificial intelligence. They were optimistic that machines would soon solve problems, understand language, and even improve themselves. Although their predictions proved overly ambitious, this conference marked the beginning of AI as an academic field. The 1950s and 1960s were filled with optimism. Many researchers believed that human-level intelligence was only a decade or two away. Early AI systems solved puzzles, played simple games, and proved mathematical theorems. These successes created excitement, but they also led to unrealistic expectations. Despite early successes, researchers quickly encountered significant obstacles. Computers were slow, memory was limited, and large datasets simply didn't exist. Many problems turned out to be far more complex than expected. As progress slowed, confidence in AI began to decline. In the 1980s, expert systems became one of AI's first commercial successes. Instead of learning from data, these systems relied on large collections of handwritten rules created by human experts. They performed well in narrow domains but were difficult to maintain and couldn't adapt to new situations. As enthusiasm faded and progress stalled, funding for AI research decreased dramatically. This period became known as the AI winter. It wasn't that AI was impossible. Rather, the available technology couldn't support researchers' ambitious goals. AI experienced two major winters, both driven by unmet expectations. A major shift occurred when researchers stopped trying to program every rule explicitly. Instead, they allowed computers to learn patterns directly from data. This new approach became known as machine learning. Rather than telling the computer exactly how to solve every problem, researchers gave it examples and let it discover patterns on its own. The rise of the Internet transformed AI research. Suddenly, companies had access to massive amounts of data from websites, smartphones, online shopping, and social media. These enormous datasets gave machine learning algorithms the examples they needed to improve dramatically. Another breakthrough came from an unexpected place: the video game industry. Graphics processing units, or GPUs, were designed to render complex graphics quickly. Researchers discovered that these processors were also excellent at performing the massive parallel computations required for deep learning. This dramatically reduced AI training times and enabled much larger models. Around the early 2010s, deep learning began outperforming previous AI approaches across many tasks. Neural networks with multiple layers achieved impressive improvements in image recognition, speech processing, and language translation. These successes demonstrated that combining large datasets, powerful hardware, and better algorithms could produce remarkable results. One of the defining moments in modern AI occurred in 2016 when AlphaGo defeated world champion Lee Sedol in the ancient game of Go. Go was long considered too complex for computers because of its enormous number of possible moves. AlphaGo's victory showed the world that AI had reached a new level of sophistication and sparked renewed interest in the field. The latest chapter in AI history is the rise of generative AI. Unlike earlier systems that mainly classified or predicted, generative models can create entirely new content, writing text, generating images, composing music, producing code, and even creating videos. This shift has made AI accessible to millions of people and transformed how individuals and organizations work and create. Looking back, AI's history is a story of ambition, setbacks, persistence, and breakthrough. The field evolved from philosophical ideas to rule-based systems, weathered periods of disappointment, and then surged forward thanks to advances in data, computing power, and learning algorithms. Understanding this journey helps explain why today's AI is so powerful, and why its progress accelerated so dramatically in recent years. Before moving on, test your understanding of the key milestones we've discussed. Focus on the why behind each event, not just the dates. Understanding why AI succeeded or struggled at different points in history will help you make sense of the technologies we'll explore next. Before diving into technical terms, let's look at the big picture. Every modern AI system, whether it's ChatGPT, a self-driving car, or a medical diagnosis tool, follows the same basic workflow. First, it collects data. Then it analyzes that data to learn patterns. Those learned patterns become a model. The model is then used to make predictions or decisions. Finally, the system can be improved using new data and feedback. Although different AI systems solve different problems, they all follow this general life cycle. Data is the fuel of artificial intelligence. Humans learn from experience, while AI learns from examples stored as data. Depending on the application, this data may consist of images, written documents, speech recordings, financial transactions, sensor measurements, or countless other forms. Without sufficient, relevant, and high-quality data, even the most advanced AI algorithms cannot perform well. It's important to distinguish between data and information. Data consists of raw facts, numbers, measurements, or observations. On their own, they don't necessarily tell us much. Information is what we obtain after interpreting that data. AI's job is to transform large amounts of raw data into useful information by discovering meaningful patterns. AI doesn't memorize every example it sees. Instead, it searches for patterns that repeat across many examples. If certain features consistently appear together, the AI begins recognizing those relationships. Once enough patterns are learned, the AI can apply them to new situations it has never encountered before. One of the most important concepts in AI is the model. A model isn't a robot or a physical machine. It's a mathematical structure created during training. When an AI learns from data, the knowledge it gains is stored inside this model. Later, when new data arrives, the model uses those learned patterns to make predictions. Training is the learning phase of AI. During training, we provide many examples along with the correct answers. Over time, the model adjusts itself until it can accurately recognize the patterns connecting the inputs and outputs. Training may take minutes, hours, days, or even weeks depending on the complexity of the model and the amount of data. Once training is complete, the model enters the inference stage. Inference simply means using the trained model to make predictions on new data. When ChatGPT answers a question or a phone unlocks using facial recognition, those systems are performing inference, not training. Features are the pieces of information AI uses to make decisions. If we're predicting house prices, features might include square footage, number of bedrooms, neighborhood, and the age of the property. Choosing relevant features is one of the most important aspects of building an effective AI system. In supervised learning, every training example includes a label. The label is the correct answer the model is trying to predict. By comparing its predictions to the true labels, the AI gradually improves during training. AI learns much like a student solving practice problems. It makes a prediction, compares it with the correct answer, measures the error, adjusts its internal parameters, and tries again. Repeating this process thousands or millions of times allows the model to become increasingly accurate. AI can only learn from the data it receives. If the data is incomplete, inaccurate, or biased, the resulting model will also be flawed. This is why data preparation often takes more time than model building in real-world AI projects. To evaluate an AI model fairly, we don't test it using the same data it learned from. Instead, we reserve separate data for testing. This tells us whether the model can make accurate predictions on examples it has never seen before. The ultimate goal of AI isn't memorization. We want the model to recognize patterns that apply broadly, allowing it to perform well on new situations. This ability is called generalization, and it's one of the defining characteristics of a successful AI system. Sometimes an AI model becomes too focused on its training examples. Instead of learning general patterns, it memorizes specific details, even random noise. This leads to excellent performance on the training data but poor results when the model encounters new information. This problem is called overfitting. The opposite problem is underfitting. Here, the model is too simple to capture the important relationships in the data. As a result, it performs poorly on both the training data and new examples. The challenge in AI is finding the right balance between underfitting and overfitting. Let's bring everything together. Every AI project follows a similar process: gather data, prepare it, train a model, evaluate its performance, deploy it into a real-world environment, and use it to make predictions. Once deployed, the system can continue to improve as new data becomes available. This complete workflow is the foundation of modern AI. This module has given you the conceptual framework for understanding how AI systems are built and used. You've learned that AI starts with data, learns patterns through training, stores those patterns in a model, and uses the model to make predictions. You've also seen why data quality, proper evaluation, and the ability to generalize are critical for success. These ideas will serve as the foundation for everything that follows in the course. Before moving on, make sure you're comfortable with these concepts. They form the backbone of modern AI and will appear repeatedly throughout the rest of the course. If you can confidently explain the AI lifecycle, the role of data, the purpose of a model, and the difference between training and inference, you are well prepared for the next module. In the previous module, we learned how AI systems learn from data. That learning process has a name: machine learning. Machine learning is a branch of artificial intelligence where computers learn patterns from examples instead of following a long list of handwritten rules. Think about teaching a child to recognize dogs. You don't write a rule saying if the ears are this size and the tail is this length. Instead, you show many examples. Eventually, the child learns the concept. Machine learning works in a very similar way. It learns by observing many examples and discovering the patterns that connect them. Traditional programming depends on humans writing every rule. For simple tasks, this works well. But what about recognizing handwriting, translating languages, or detecting fraud? The rules become far too complex. Machine learning reverses the process. Instead of writing the rules, we provide data and the correct answers. The computer discovers the rules on its own. This ability to learn makes machine learning suitable for problems that are difficult or impossible to solve with fixed programming logic. Machine learning powers many of the intelligent systems we interact with every day. Banks use it to detect suspicious transactions. Online retailers use it to recommend products. Hospitals use it to assist with diagnoses. Streaming services personalize recommendations, and self-driving cars use machine learning to understand their surroundings. These systems all share the same principle: learning useful patterns from data. Although machine learning includes many algorithms, most fall into three broad categories. Supervised learning uses labeled data to learn correct answers. Unsupervised learning explores unlabeled data to discover hidden patterns. Reinforcement learning learns through trial and error using rewards and penalties. We'll explore each type in detail over the next few slides. Supervised learning is the most common type of machine learning. During training, every example includes both the input and the correct answer. The model learns the relationship between them. Over time, it becomes capable of predicting the correct answer for new examples it has never seen before. Classification is a type of supervised learning where the goal is to assign an item to a category. Every prediction belongs to one of several predefined classes. Email filtering, medical diagnosis, and facial recognition all rely heavily on classification models. Unlike classification, regression predicts continuous numerical values. Instead of asking which category, regression asks how much. Predicting house prices or estimating tomorrow's temperature are common regression problems. Sometimes we don't know the correct answers in advance. In these situations, unsupervised learning searches for structure within the data itself. The model groups similar items together based on shared characteristics, often revealing insights that humans hadn't noticed. Clustering is one of the most common unsupervised learning techniques. Imagine an online retailer with millions of customers. Instead of manually defining customer groups, clustering automatically discovers people with similar purchasing habits. Businesses use these groups to personalize marketing, improve recommendations, and better understand customer behavior. Some datasets contain hundreds or even thousands of features. Dimensionality reduction simplifies these datasets by preserving the most important information while removing redundancy. This can improve performance, reduce computation, and make complex data easier to visualize. Reinforcement learning takes a different approach. Instead of learning from labeled examples, the AI learns by interacting with an environment. Every action leads to a reward or a penalty. Over time, the system discovers which actions maximize long-term success. This approach has been used in robotics, game playing, and resource optimization. Imagine teaching a robot to walk. No one programs every joint movement. Instead, the robot experiments, receives feedback, adjusts its strategy, and gradually improves. This process mirrors how reinforcement learning systems learn through experience. In professional machine learning, datasets are often divided into three parts. The training set teaches the model. The validation set helps fine-tune it. Finally, the test set measures how well the finished model performs on unseen data. Keeping these datasets separate helps ensure that performance measurements are reliable. Building a model is only part of the process. We also need to measure how well it performs. Accuracy tells us how often the model is correct, but it isn't always enough. In areas such as healthcare or fraud detection, precision and recall often provide a more meaningful picture of performance. Selecting the right evaluation metric depends on the problem you're trying to solve. The confusion matrix provides a detailed view of classification performance. It shows not only how many predictions were correct, but also the types of mistakes the model made. Understanding these errors helps developers improve models and choose appropriate evaluation metrics. Two important concepts in machine learning are bias and variance. A model with high bias is too simple and misses important patterns. A model with high variance is too complex and memorizes the training data. The goal is to strike a balance where the model captures meaningful relationships without overfitting. Let's bring all the pieces together. Every machine learning project begins with a real-world problem, followed by data collection and preparation. The model is trained, evaluated, deployed, and continuously monitored to ensure it performs well over time. This workflow is the foundation of professional machine learning practice. In this module, you've explored the core ideas behind machine learning. You now understand how machines learn from data, the different types of learning, common problem types, and how models are evaluated. These concepts are essential because they underpin many of the AI systems we use every day. Before continuing, take a moment to answer these questions. They reinforce the core concepts that you'll build on in the next module. If you can clearly explain the differences between supervised, unsupervised, and reinforcement learning, and between classification and regression, you've developed a strong foundation for understanding deep learning. So far, we've focused on the broader field of machine learning. In the next module, we'll explore one of its most powerful branches, deep learning. You'll discover how neural networks are inspired by the human brain, why they revolutionized image recognition, speech processing, and language understanding, and how they laid the groundwork for technologies like ChatGPT and modern generative AI. This is where the story of modern AI becomes even more exciting. In the last module, we learned about machine learning. Deep learning is simply a specialized type of machine learning, but it's also the technology responsible for many of the biggest AI breakthroughs of the last decade. Traditional machine learning often relies on humans to decide which features are important. Deep learning can learn many of those features automatically from raw data. This ability allows deep learning to solve problems that were once considered impossible. The word deep refers to the number of layers inside a neural network. Early neural networks had only one or two hidden layers. As computing power improved, researchers built networks with dozens, or even hundreds, of layers. These deeper networks can learn increasingly complex patterns, from simple edges in an image to complete objects and scenes. Deep learning takes inspiration from the human brain, which consists of billions of interconnected neurons. Artificial neural networks borrow the basic idea of many simple units working together. However, it's important not to take the analogy too far. Artificial neurons are mathematical functions, not biological cells, and they operate in a much simpler way. The artificial neuron is the basic building block of a neural network. It receives one or more inputs, gives each input a level of importance using weights, combines them, and then decides whether to pass a signal to the next layer. Individually, neurons are simple. But when millions of them work together, they can recognize incredibly complex patterns. Not every piece of information is equally useful. Weights tell the model which inputs matter more for a given prediction. During training, the model continuously adjusts these weights until it finds the combination that produces the most accurate results. After combining its inputs, a neuron applies an activation function. You can think of this as a decision gate. It determines whether the information is strong enough to continue through the network. Different activation functions have different characteristics, but their purpose is the same: to help the network learn complex relationships. A neural network is organized into layers. The input layer receives raw data. Hidden layers gradually transform that data by learning increasingly complex patterns. Finally, the output layer produces the prediction. Each layer builds on the work of the previous one. One of the most fascinating aspects of deep learning is how it learns hierarchical features. In image recognition, early layers detect simple edges and lines. Middle layers combine those into shapes and textures. Later layers recognize complex objects such as faces or animals. This layered learning process allows deep networks to understand extremely complicated data. During prediction, information moves through the network from the input layer to the output layer. Each layer transforms the information before passing it to the next one. This process is called forward propagation, and it produces the model's prediction. After making a prediction during training, the model compares it with the correct answer. The difference between the prediction and reality is called the error or loss. This error tells the network how much it needs to improve. Once the error is known, the network works backward to determine which weights contributed most to the mistake. It then adjusts those weights slightly, making the prediction a little better next time. This process is called backpropagation, and it's one of the key innovations that made deep learning practical. Gradient descent is the optimization process used to improve a neural network. Imagine standing on a foggy mountain and trying to reach the lowest point. You can't see the entire landscape, so you take small steps downhill. Gradient descent works in a similar way, making gradual improvements until the model reaches a solution with low error. Large datasets are rarely processed all at once. Instead, they're divided into smaller groups called batches. Once the model has processed every batch, it has completed one epoch. Training typically requires many epochs before the model converges to a good solution. Training deep neural networks requires enormous computational power. Graphics processing units, or GPUs, excel at performing many calculations in parallel, making them ideal for deep learning. Without GPUs, many of today's AI breakthroughs would have taken far longer to achieve. Convolutional neural networks, or CNNs, are designed specifically for visual data. They excel at recognizing patterns in images by learning features such as edges, textures, and objects. CNNs revolutionized computer vision and remain widely used in image-related tasks. Recurrent neural networks were designed to process sequential information, where the order of data matters. They became popular for language translation, speech recognition, and time series forecasting. However, they struggled with long sequences, leading researchers to develop more powerful alternatives. Transformers represent one of the biggest breakthroughs in AI history. Unlike earlier models, transformers can process entire sequences simultaneously while focusing on the most relevant information using a mechanism called attention. This architecture powers ChatGPT, modern translation systems, and many of today's most advanced AI models. Deep learning is already transforming industries around the world. From voice assistants and recommendation engines to autonomous vehicles and medical imaging, neural networks are solving problems that once seemed beyond the reach of computers. Their ability to learn directly from complex data has made them the dominant approach in many AI applications. Deep learning has several key strengths. It can learn highly complex relationships, work directly with images, audio, and text, and automatically discover useful features. These capabilities have led to impressive performance across a wide range of AI tasks. Despite its success, deep learning isn't perfect. Training large models requires enormous datasets, powerful hardware, and significant time. In addition, deep networks can be difficult to interpret, making it challenging to explain why a particular prediction was made. These limitations are active areas of research. This module introduced the core ideas behind deep learning. You've seen how neural networks learn, how they improve through feedback, and why architectures like CNNs and transformers have transformed AI. These concepts provide the technical foundation for understanding modern generative AI systems. Before moving forward, make sure you're comfortable with the concepts we've covered. Understanding how neural networks learn and why different architectures exist will make the next module much easier. Next, we'll explore generative AI, the technology behind ChatGPT, AI image generators, coding assistants, and many of the tools that have brought AI into everyday life. You'll learn how these systems generate text, images, and other content, and why large language models have become one of the most exciting developments in modern AI. Up to this point, we've mostly discussed AI systems that classify, predict, or recognize patterns. Generative AI goes a step further. It creates something entirely new. Instead of simply identifying a cat in a picture, it can generate a brand new image of a cat. Instead of classifying text, it can write an essay, summarize a report, generate software code, or compose music. This creative capability is what has made generative AI one of the fastest-growing technologies in history. A large language model, often called an LLM, is a type of deep learning model trained on enormous collections of text. During training, it reads books, articles, websites, and many other text sources. By analyzing these examples, it learns grammar, facts, writing styles, reasoning patterns, and relationships between words. It doesn't memorize every sentence. Instead, it learns statistical patterns that allow it to generate new, coherent text. One of the most surprising ideas behind modern language models is also one of the simplest. At their core, LLMs are prediction engines. They look at the text you've already provided and predict what token is most likely to come next. By repeating this prediction thousands of times every second, the model generates entire sentences, paragraphs, and even books. Although we think in words, language models work with tokens. A token is a small unit of text. Sometimes it's a whole word. Sometimes it's part of a word or even punctuation. Breaking text into tokens allows the model to process language more efficiently and handle many different languages using the same underlying approach. Computers don't understand words directly, they understand numbers. Embeddings transform words into numerical representations that capture meaning. Words with similar meanings end up close together in this mathematical space. This allows the model to recognize relationships such as countries and capitals, professions, or synonyms without storing explicit rules. When you talk to an LLM, it doesn't remember everything forever. Instead, it can only consider a limited amount of text at one time. This is called the context window. Larger context windows allow models to understand longer conversations, analyze lengthy documents, and maintain consistency across complex tasks. Imagine reading a sentence. Your brain naturally focuses on the words that matter most for understanding the meaning. Transformers use a mechanism called attention to do something similar. Attention allows the model to weigh the importance of different words in relation to one another, making it much better at understanding context than earlier language models. Training a large language model is one of the most computationally intensive tasks in AI. These models are trained on enormous text datasets using thousands of powerful GPUs over weeks or even months. During training, the model gradually adjusts billions of parameters until it becomes highly effective at predicting the next token. After completing broad training, organizations often fine-tune a model for specific tasks or industries. A hospital may adapt a model for medical terminology, while a law firm may fine-tune one for legal documents. Fine-tuning helps the model perform better in specialized domains while building on its existing knowledge. LLMs respond based on the information you provide. A vague prompt often produces a vague answer. By giving clear instructions, relevant context, specific constraints, and the desired output format, you guide the model toward more useful responses. This practice is known as prompt engineering. One limitation of language models is hallucination. A hallucination occurs when the model generates information that sounds convincing but is inaccurate or entirely fabricated. This happens because the model is predicting likely text, not verifying facts in real time. For this reason, important information should always be checked against reliable sources. One way to reduce hallucinations is through retrieval-augmented generation, or RAG. Rather than relying solely on what it learned during training, the model first searches trusted documents or databases for relevant information. It then uses those retrieved sources to produce a more accurate and up-to-date answer. A chatbot mainly responds to questions. An AI agent goes further. Agents can plan tasks, decide what information they need, use external tools, and carry out multiple actions to achieve a goal. For example, an agent might search the web, compare hotel prices, check your calendar, and draft an itinerary, all as part of a single request. Early AI systems were designed for one type of data. Modern models are increasingly multimodal. They can understand and generate text, analyze images, interpret audio, and even process video. This ability allows a single model to perform a much wider variety of tasks. Generative AI is already transforming how people work. Writers use it to draft content, developers generate code, designers create images, teachers prepare lesson plans, and businesses automate customer support. Rather than replacing human creativity, these tools often act as collaborators that speed up routine tasks and inspire new ideas. Generative AI is remarkably capable, but it's not infallible. It excels at generating ideas, summarizing information, translating languages, and assisting with creative work. However, it can also make mistakes, reflect biases present in its training data, or produce outdated or inaccurate information. The most effective approach is to view AI as a powerful assistant rather than an unquestionable authority. Congratulations, you've just completed one of the most important modules in the course. You now understand the core ideas behind modern generative AI and large language models. More importantly, you can explain concepts like tokens, attention, embeddings, context windows, and RAG without needing to dive into complex mathematics. In the next module, we'll shift from how AI works to how AI is used, exploring real-world applications across healthcare, finance, education, manufacturing, transportation, and many other industries. This will show how the technologies you've learned about are creating value in the real world. One of the biggest misconceptions about AI is that it's something we'll use in the future. In reality, AI is already part of our daily routines. Every time you search the web, receive a personalized recommendation, unlock your phone with facial recognition, or ask a virtual assistant a question, AI is working behind the scenes. In this module, we'll explore how these technologies are transforming industries around the world. Healthcare is one of the fields where AI has the potential to make the greatest impact. AI systems can assist doctors by analyzing medical images, identifying patterns that may indicate disease, and helping prioritize urgent cases. Researchers also use AI to accelerate drug discovery and personalize treatments based on patient data. It's important to remember that in most cases, AI supports healthcare professionals rather than replacing them. Financial institutions process millions of transactions every day. AI helps identify unusual patterns that may indicate fraud in real time. Banks also use AI to assess credit risk, automate customer support, forecast market trends, and detect suspicious financial activity. By analyzing vast amounts of financial data, AI helps organizations make faster and more informed decisions. Modern factories increasingly rely on AI to improve productivity and reduce costs. Sensors monitor equipment continuously, allowing AI to predict when machines are likely to fail before costly breakdowns occur. AI also helps inspect products for defects and optimize production schedules and supply chains. Online retailers use AI to personalize nearly every part of the shopping experience. Recommendation systems suggest products based on browsing history, while AI forecasts demand, manages inventory, and supports customers through virtual assistants. These capabilities help businesses improve customer satisfaction while increasing operational efficiency. Education is becoming more personalized through AI. Intelligent tutoring systems adapt lessons to each student's pace and learning style. Teachers use AI to automate repetitive tasks such as grading, freeing more time for instruction. AI also supports language learning, accessibility, and the creation of educational content. AI plays a major role in transportation, even if you never ride in a self-driving car. Navigation apps predict traffic, optimize routes, and estimate arrival times using real-time data. Logistics companies use AI to improve delivery routes and manage fleets, while autonomous vehicle research continues to advance. Agriculture is becoming increasingly data-driven. AI analyzes satellite imagery, drone footage, and sensor data to help farmers monitor crop health, detect diseases early, and optimize the use of water and fertilizers. These technologies can improve yields while reducing environmental impact. Cybersecurity teams face millions of security events every day. AI helps by identifying patterns that may indicate malicious activity. It can detect unusual behavior, prioritize alerts, and assist security professionals in responding to threats more quickly. While AI strengthens defenses, attackers also use AI, making cybersecurity an ongoing race between defense and offense. Entertainment companies use AI to recommend movies, songs, podcasts, and games based on user preferences. AI also supports content creation, from video editing to visual effects and script assistance. In gaming, AI controls non-player characters and creates more dynamic experiences. Businesses across industries are using AI to automate repetitive work and support decision-making. AI can summarize reports, analyze documents, forecast demand, and assist customer service teams. Rather than replacing every employee, these tools often free people to focus on higher-value work. Cities are becoming smarter by combining AI with sensors and connected infrastructure. AI helps optimize traffic signals, monitor energy use, improve public transportation, and detect maintenance issues before they become serious problems. These technologies aim to improve quality of life while using resources more efficiently. Scientific research increasingly depends on AI to analyze complex datasets that would be impossible for humans to process manually. Researchers use AI to identify new materials, model climate systems, analyze astronomical observations, and accelerate discoveries in biology and medicine. AI acts as a powerful research assistant, helping scientists explore ideas more quickly. While AI offers enormous opportunities, implementing it successfully requires careful planning. Organizations need high-quality data, skilled teams, and responsible governance. They must also address ethical considerations, security risks, and regulatory requirements. Successful AI adoption is about more than technology, it's about people, processes, and trust. AI isn't just for large technology companies. Every learner should think about how these tools might apply to their own role or industry. Consider the repetitive tasks you perform, the decisions you make, and the information you analyze. AI may not replace your expertise, but it can often help you work more efficiently and focus on higher-value activities. This module has shown that AI is not limited to a single industry or profession. From healthcare and finance to agriculture and scientific research, AI is becoming a foundational technology across the global economy. As you continue your AI journey, start looking for opportunities to apply these ideas in your own work and daily life. In the next module, we'll explore one of the most important topics in AI today: ethics, risks, and responsible AI. We'll discuss fairness, bias, privacy, transparency, and the societal impact of AI, topics that are essential for anyone who wants to use AI responsibly. Throughout this course, we've explored how AI works and where it's used. But with great capability comes great responsibility. AI systems increasingly influence decisions about healthcare, finance, education, hiring, and public services. Because of this, we must think not only about what AI can do, but also about how it should be designed and used. Responsible AI is about building systems that people can trust. AI systems learn from historical data. If that data contains unfair patterns or underrepresents certain groups, the model may produce biased outcomes. Bias doesn't always come from the algorithm itself. It can also come from how data is collected, labeled, or used. Recognizing and reducing bias is an ongoing challenge for AI developers and organizations. Fairness means designing AI systems that perform well across different groups and avoid unjust outcomes. There isn't always a single definition of fairness, which is why organizations often evaluate models from multiple perspectives. Fairness requires continuous monitoring, testing, and improvement, not just good intentions. Many AI systems rely on large amounts of data, some of which may be personal or sensitive. Organizations have a responsibility to protect that information through strong security practices, thoughtful data governance, and compliance with applicable privacy requirements. Users also benefit from understanding how their data is collected and used. Some AI systems, especially deep neural networks, can be difficult to interpret. Explainability aims to provide understandable reasons for an AI's output, helping users evaluate whether the result is appropriate. In areas such as healthcare and finance, being able to explain important decisions can support trust and accountability. AI is a powerful tool, but it isn't infallible. In many high-impact situations, human oversight remains essential. Professionals can review AI recommendations, consider additional context, and make final decisions when appropriate. Human judgment and AI capabilities often complement each other. AI is changing the nature of work. Some routine tasks are becoming automated, while new opportunities are emerging in AI development, governance, operations, and oversight. Historically, technology has both displaced certain tasks and created entirely new industries. AI is likely to continue that pattern, although the pace and impact may vary across sectors. Generative AI can produce highly realistic content, including images, audio, and video. While these tools have many positive uses, they can also be misused to create deceptive or misleading content. Developing media literacy and verifying important information are increasingly valuable skills in the age of AI. AI safety focuses on ensuring that systems behave as intended, especially when deployed in real-world environments. This includes testing models thoroughly, monitoring performance, protecting against misuse, and updating systems when problems are identified. Safety is not a one-time activity, it continues throughout the AI lifecycle. Governance provides the structure for managing AI responsibly within an organization. It defines who is responsible for AI systems, how risks are assessed, how decisions are documented, and how models are reviewed over time. Good governance helps organizations use AI consistently and responsibly. AI continues to evolve rapidly. We are seeing progress in multimodal models, increasingly capable AI agents, more efficient models that run on smaller devices, and AI-assisted scientific research. While it's impossible to predict every breakthrough, it's clear that AI will continue to shape technology, business, and society. Popular media often creates unrealistic expectations about AI. While today's AI is remarkably capable, it does not possess human understanding, consciousness, or perfect knowledge. Separating myths from reality helps us make informed decisions about when and how to use AI. AI will continue to change how we work and learn. Rather than trying to predict every future development, focus on building adaptable skills. Understanding AI concepts, thinking critically, communicating effectively, and learning continuously will remain valuable regardless of how the technology evolves. Congratulations on reaching the end of the course. You began by exploring the origins of AI, then learned how machines learn from data, how neural networks power deep learning, how large language models generate text, and how AI is transforming industries worldwide. Finally, you've considered the ethical and societal responsibilities that come with these powerful technologies. You now have a strong conceptual foundation to understand and discuss modern AI with confidence. Take a few minutes to answer these questions without looking back at your notes. If you can explain these concepts in your own words, you've achieved the main goal of this course, understanding how AI really works and how it is shaping the world around us. Congratulations on completing this course. You now have a clear understanding of the foundations of artificial intelligence, from its history and core concepts to machine learning, deep learning, generative AI, and the ethical considerations that accompany these technologies. This is only the beginning of your AI journey. Continue exploring, stay curious, and remember that the field evolves quickly. The strongest AI practitioners are those who combine technical understanding with critical thinking and responsible use. Thank you for learning with me. I wish you continued success as you explore the exciting world of artificial intelligence.